Okay, hello everyone. So we are continuing. So we are pleased to welcome our new speaker, Andrea Montanari, who is professor at Stanford. I know Andrea doesn't like long introductions, so I won't give one. We'll just say that he is no stranger to Les Houches. He's been here many times. And in fact, when he was here in 2006, we had a discussion about colorful project, and we had a nice paper together with Lenka at the time. So Andrea, it's a pleasure to have you here, and you have the floor.
Okay. Okay, thanks for the short introduction, and thanks everybody for being here. It's always nice to be in Les Houches. Okay, these lectures will be about supervised learning. So I must say I don't have a very clear idea of what is the background of all of you, so I might be very boring at the beginning for some of you, but okay, carry on with me. So what is the problem? We have data that are yi, xi. The yi are responses, and xi's are covariates or feature vectors, and you have n of them, and they are IID with some common distribution P on this space. And what we want, I want a model that is a function from Rd to R to predict a new response from a new covariate vectors. And ideally, I would like to minimize the error, the expected error on a new test point. So this is called test error. And so this is R for a certain model F. This is just the expectation. And here I should put a loss function, but let's say that we'll take square loss. In fact, in all of this lecture, I'll take square loss. And here, y nu x nu is the same distribution as yi xi. And okay, of course, trivial remark, if I knew the distribution here, so if I knew P, then things would be easy. I would just take f of x equal the conditional expectation of y given x. So let's call this f star, and this, of course, minimizes the risk. For each f, with strict inequality, if f star is not, if f is equal to different from a star. Okay, so what is the standard example of how to do this thing that we have in mind is empirical risk minimization. Empirical risk minimization, of course, means that you minimize the empirical risk. So instead of minimizing the population error, you minimize r hat n, that is 1 over n sum over I less than n yi minus f of xi. Of course, I cannot do this without putting a constraint, because otherwise I can take any function that is equal to the yi on the point xi and 0 otherwise. And so I have to put a constraint. So I have to say that f is in some restricted function class. So this is a function class. Okay, so this is one thing. Okay, so this is the basic problem of supervised learning. Is everybody okay with the setting? Okay, so I want to say one. I don't like philosophizing too much, but I want to say one word about what is okay and what is less okay in this war. So of course, this problem, when we don't want to do math about it, we have to make some assumptions about this distribution P. Okay, and the philosophy of this lecture, and my philosophy in general in this area, is the following: that is, you can make two assumptions on P for two reasons. One is to construct the algorithm f hat. Okay, So you can say, I know what is something about this distribution P, and I'll use it in the construction of the algorithm. And this is not really okay. Or not so okay. And on the other hand, to do theory, I think this is okay. Ideally, I don't want to make assumptions, but I'll accept if I need to make assumptions to do math. Okay, so for instance here, this method is completely oblivious to what is the distribution P. But then if I want to analyze it, okay, I might have to make assumptions about what is the distribution P. Okay, so this is the setting. Now, one word about what I will focus on. I will focus on parametric classes of functions. So f of x will be mostly parametric. So this will depend. Okay, here there is an abuse of notation, but this means that really, f depends on a bunch of parameter theta. Theta will be a vector of parameters. P will be the number of parameters. And I'm really interested in either the number of parameters to be much larger than the number of sample points. Okay, so this is what I call sometimes the overparameterized case, or the number of parameters clearly infinity. So this is what's called typically the non-parametric case. Okay, so let me say perhaps why we are interested in the number of parameters so large. So this type of models. Why? So you have listened to Nati's lecture, so probably has already drilled this down in your brain. But first of all, neural networks are parametric models. And they are often overparameterized. And okay, let me stop it here. And they are often overparameterized. Now, these thing, the focus of non-parametric overparameterized model is not new. In fact, models with a lot of parameters are quite classical, and here is probably the most classical example. Most classical example is probably the spline. So let's take the cubic spline. Okay, so let's do a check whether how many of you know what splines are. Everybody, fantastic. So okay, so it can be very quick. So in this case, xi, yi, reals times reals. Okay, and what is a spline? A cubic spline is the following thing. You minimize the train error with a regularization that is the square of the second derivative of f. Okay? Or equivalently, you minimize the train error subject to what? F, let's say f second square integral dx less than some rho. Okay, these are two equivalent formulations. So this is more similar. This is actually the same formulation as this one, and this is just the penalized version of this. Okay, so what is new here? So this is focusing on over-parameterized or non-parametric model is of course not new. Splines have been studied for half a century or more than that, surely more than that. But what is new is that we will take so in this spline example, for instance, we'll take lambda to 0. Okay, or equivalently, we'll look at rho going to rho star. That is the first radius, the first value of this norm at which R of n of f is 0. So the value here will be 0. Okay, so so what does this give in the spline world, for instance? So in the spline context, this means the following, that what we'll be doing is the following. Suppose that you have, for instance, data points that are really equal to some coefficient times xi plus epsilon I, so this is noise. So they basically, in theory, would be aligned to a line, but there is some noise on top. This is x1, y1. So the way we'll fit these data points is, perhaps I'll color them. The way we'll fit these data points is, in the spline world, what does it mean to fit a spline? Means that I'll construct what? A polynomial, a third-order polynomial that has continuous derivative everywhere. So something like this. Okay. So this is, there is no doubt. It's quite intuitively clear that this is not a good idea. Why it's not a good idea? If you try to think a little bit about it, why it's not a good idea? Well, these are my train points. Suppose that somebody gives me a test point, right? So a test point will have the same distribution as the train point. So with some non-negligible probability, will be very close to the train point. Say this is x2, y2. So with some non-negligible probability, the test point, x nu, will be here. Okay? So if my model is the yellow one, when I test at this point, I will predict this value, and this is completely off, right? It's off by a value, by an amount that is proportional to the standard deviation of the noise. Okay, so if epsilon I, for instance, are sigma square, this will be off by an amount that is of order sigma. Okay, so the prediction error will be large for this interpolating spline. So this is why if you look at a classical paper or any paper, any textbook on splines will tell you that you have to take a regularizer that is non-zero, or you have to take a rho that is not the maximal possible rho. And in fact, one can prove these kind of things, and that this is not a good idea. For instance, there is a nice paper by Sasha Raklin and Jai that proves that this is suboptimal. It's not in the context for spline, but for a certain kernel method, but it's the same. So this is 2018. Proves really formally that this is suboptimal. Okay. Okay, nevertheless, people, so you know, in deep learning, machine learning, people in machine learning world, people have been ignoring this standard knowledge, and they have been largely working with over-parameterized model, not regularizing them so well. And so in this context, what happens is that often you achieve test error much bigger than train error, and still the test error is good. Whatever that means.
Just briefly about the terminology. Do we really need P much bigger than N to be over-parameterized? Couldn't we have some case where P is still smaller than N and you're still over-parameterized? Or does that matter?
Okay, so what is the boundary between over-parameterized and under-parameterized? I would say that the boundary is really where the trainer, I would call over-parameterized a model that you train in such a way that the train error becomes basically zero.
Okay.
Right? Or much smaller than the null model, right? Right. So this might not, you know, you might have P of the same order of N or P bigger than, you know, if you are doing, for instance, binary classification, when P is bigger, linear binary classification with P is bigger than what, 2N, or N over 2, then it becomes. Okay, so people have been doing this, so under-regularizing and, you know, driving the test error, the train error to very small value, and this worked. And okay, what is the hypothesis here? Why this worked so well in deep learning is that, okay, you lose this classical theory, but you gain tractability. So what is the hypothesis is that the reason why people ignored the classical prescription or the classical statistical theory is that, you know, they were mainly interested in optimizing this network, and so they over-parameterized in such a way to be able to, you know, run gradient descent, stochastic gradient descent, and you know, they found out empirically that over-parameterized this simplified the convergence of SGD. So what is the picture, the mental picture that I have in mind is that there is the space of parameters, and perhaps in this space there is a very high dimensional submanifold that is the submanifold of global empirical risk minimizer, so it's the space of theta such that fxi theta equal yi for each I. So it's the space of models, the manifold of models that perfectly interpolate the data. And what's really happening is that since this green submanifold is very large, when you start gradient descent at a random point, you converge very quickly to a solution. So GD, so this is, so GD or SGD converges to a point in this submanifold. All right, so this is kind of the philosophy here. So this is the philosophy of why we are interested in over-parameterized models, you know, under-regularized, and how this explain the convergence of SGD. Now, so we would like to understand how is it possible, one puzzle is how is it possible that such models still generalize well. And the reality is that there is only one special or one corner case in which we understand this well, and this is the linear or lazy or neural tangent regime. Okay, so this will be really the focus of my lectures, not because there is not other specific examples in which we can demonstrate some pieces of this picture, but this is the only case in which the whole picture is more or less clear. Yeah.
The general
Well, for instance, it might mean that, so you will see in a specific example, it might mean, for instance, that the test error is close to the optimal test error, to the optimal test error that you can achieve from those n data points. So what does close mean? Well, it might mean that is equal to the optimal test error plus small of 1, things that go to 0. Or that can be that has the right rate of going to 0 with n of d, or that simply goes to 0 in some way. Okay? Even that is quite surprising, right? In this case, for instance, you see that the test error in this method, what's bad is that I increase the number of data points in this example, and still the test error will stay equal to sigma. Okay? And that's not good. This is the test error. I'll use interchangeable the test error for two things, right? Sometimes you look at what I wrote, and sometimes you look at the excess test error. So the test error over the optimal predictor. The two differ just by a constant, an additive constant. So as you see here, this excess test error is still big. Right? It's still a constant, even if you give me a humongous number of data points. So that is what's clearly bad about this method in low dimension. Any question? Okay, so let me start from So I'll mostly be talking about generalization, but I want to start by saying something about this linear or lazy regime and show what it is about, because I don't think this has been done by anybody. So I want to ask a simpler question. So is there theta? So call this manifold, okay, ERM0, the set of global empirical risk minimizer or interpolators near theta 0. So I initialize my gradient descent at a point theta 0, and I want to ask, is there an interpolator near to this point? If that picture and intuition is correct, then there should be. Okay, so this is the question, and let me it's convenient piece of notation. So this I destroyed something. This depends on the model only through the following map. Okay, so I'll define a map from Rp to Rn that is just Fn at theta is just f at x1 theta xn theta. So this is the evaluation of my model at the n data points, right? And the question, what I want to do is I want to solve y equal fn of theta, where y is just the vector of all responses. So you want just to solve an overdetermined set of nonlinear equations, right? Now, we are looking for a solution near theta 0, so it makes sense to subtract fn of theta 0. And then makes sense to Taylor expand. Since I'm assuming that theta is close to theta 0. And then there is a remainder of the Taylor expansion that is So let me call theta t to be theta minus theta 0 plus t times theta minus theta 0. All right, so I didn't do anything, right? I just wrote this integral. df is just the Jacobian of the differential of that map, right? Okay, so let me give me names to this object. So let me call this y tilde. I'll call this phi. All right, so what is phi is really a matrix that is n by p. Is the Jacobian at the initialization, and let me call this error E of theta. What? Here is theta, right? Because here I'm just, this whole thing is d fn of theta t in dt. Right. Doesn't matter in the end. Okay, so I want to bound, ideally I want to, theta is close to theta 0, so I want to bound this difficult term. And so I will make an assumption, I will make a definition or assume. So I'll define this Lipschitz constant, that is d fn of sup over theta, d fn of theta minus d fn of theta 0 operator norm divided by theta minus theta 0 2. And let's say that this is finite. Okay, so if this is true, then this is kind of a bound on the second derivative. So you can bound this by theta minus theta 0. So under that assumption, E of theta to norm is less than ln times theta minus theta 0 to square. Okay, and now what I want to solve is I want to solve y tilde equal phi times theta minus theta 0 plus this error. Okay, so I invert, so I'll write theta equal theta 0. And then to invert phi of course is not invertible because it's a rectangle, it's a fat matrix, but I can take the pseudo inverse. So phi dagger means the pseudo inverse of phi, y tilde, right? So this would be if I didn't have the error term. Right? And the error term gives a correction that is this one. Okay? So why the pseudo inverse in particular? Well, because I'm looking for a solution that is as close to theta 0 as possible, and so this is the solution that makes this term of the smallest possible L2 norm. Okay, excellent. So now I still have the nonlinearity. So let me call this delta. So delta is equal to phi dagger of E of theta 0 plus phi dagger y tilde minus delta. Okay, so let me give a name to this. I'll call it f of delta. So I want to find a fixed point of this map, capital F. I want to find a fixed point of this map, capital F. And of course, if F maps a ball of radius r, so this is the ball of a radius r in Rp, to a ball of radius r prime with r prime less than r. Okay, so if it decreases the radius, if it, delta, I hope that is smaller, right? So if this map F maps this ball in a smaller ball, then I can be sure that it has a fixed point. So I'll be happy. Then star has a fixed point. With delta less than r prime. Okay, so what I need to do is just bound this norm. Okay, so let's do it. This is less or equal, then, okay, there will be the norm of the pseudo-inverse, the operator norm of a pseudo-inverse. The operator norm is the largest singular value, right? Times, and then I have my assumption on E, this constant, the second derivative ln, times the square of the norm of whatever is inside, minus theta 0. By tilde minus delta 2 square. Okay, very good. And now I can do triangular inequality here. So this is r prime is less or equal. So this is, I'll assume a bound here, and so I get a bound on the norm here. The operator norm of phi dagger times ln times phi dagger y tilde 2 plus r square. I'm doing just simple. I mean, the most sophisticated thing that I did is probably triangular inequality.
Before you erase it, can you maybe comment back, why do you expand this way with the interval?
How would you expand? Taylor expansion, right? I want to do g of t. How do you do the Taylor expansion? This is g of 0.
But where is the t coming from? Sorry,
Okay. G of x, g of 0, plus x g prime of 0, plus, and now how do I do it? Integral between 0 and x, g prime of u, minus g prime of 0 du. Okay? But I can also call this integral between, now when u is a vector, integral between 0 and 1 of g prime of t times x minus g prime of 0, and then there is an x times du. G prime, d in dt. G prime of x. Okay, there is a factor, but...
Okay, that's the remainder. And you're going towards showing that the remainder will not matter? Or?
Yeah, I'm sure, I mean, yeah, okay. So this is what I did. This is the remainder, okay? I assume this Lipschitz condition on the Jacobian, right? This implies that the remainder is bounded, is quadratic with this coefficient. So think of ln as a bound on the second derivative. So ln really quantifies how nonlinear is my model, right? So this is the bound on the second derivative. Fine. And now I'm psychologically I'm thinking of this as a small error. So I put it here, and now I try to find the fixed point of this recursion. Right? And now here I use my bound on the error. Now if I find now an R such that this right-hand side, so let's call this R prime, or I can define R prime to be this way, R prime of R. Okay. If I can find R such that this is less than R, then I'm in business, right? So R prime of R has the form whatever A plus B times B plus R square, where A is something and B is something else. If there exists an R positive such that R prime of R less than R, I'm done. Okay, now, this is a simple undergraduate calculus exercise, and turns out that this is true, holds if, if the following holds, Ln times phi dagger operator norm times phi dagger y tilde operator norm is less than 1/4. Okay? And now I can simplify this a little bit. So this is bigger or equal than, so okay, if Ln times phi dagger, so it's sufficient, operator norm square times y tilde 2 norm less than 1/4. And this again is the largest singular value of the pseudo inverse is 1 over the minimum singular values of the matrix. So this is if and only if Ln times y tilde is less than sigma min of phi square divided by 4. Okay, so let's look a little bit a second at this. Does this make sense? Yeah, well, it does, because what I want Ln that says how nonlinear is my model to be small. Well, I'm approximating by a linear model. This will work out if Ln is small. And I want, this is what is the Jacobian at the initialization to be non-singular. And it makes sense, because if the Jacobian at the initialization is singular, then the linear approximation is probably not a good idea. Okay, so in fact, under this condition, a lot more can be proved. So under this condition, there exists one solution. You can bound, of course, theta minus theta 0. Under this thing, all right? So what we have is that if this is ERM 0, what we did is that we started at some theta 0, and we found that there is a solution, an interpolator close to theta 0, and intuitively it makes sense that gradient descent should converge quickly, and in fact this can be proved. Okay, so much more can be proved. And okay, so this is a theorem. So there are at least, I don't know how many. I lost count of how many versions of this theorem there exist. Perhaps 5 or perhaps 10. But the first version was in a paper by Du et al. I think 2000. Okay. all references in these lectures will be by memory, so the years might be wrong by ±1. So assume, so let me give a name to this right-hand side. I'll call this lambda 0. So assume this condition holds. Then what these people prove is one, that Rn of theta t. So what is this? Theta t is I run gradient flow starting at theta 0. So I take initialization theta 0, and then I run the gradient flow in the empirical risk. There are versions of this for gradient descent. There are versions for stochastic gradient descent. But let's say that we do gradient flow, so that this is less than. So under this condition, gradient flow converges, and this is for all t. Convergence, exponentially fast to 0, to a global empirical risk minimizer. So this part of the theorem is saying that this converges quickly to this manifold. Okay, and 2.
You're assuming over parameterization.
Sorry?
Are we assuming over parameterization?
So as I said, over parameterization here means, or I'll take it to mean that there exist models in my class that achieve 0 empirical risk, right? That perfectly interpolate the data. And actually this proves that it's over-parameterized because it shows that there exists a point. In fact, we did prove it. I proved it in front of you, that under this condition, the model is over-parameterized. Not only is over-parameterized, but there is a solution very close to an interpolator, very close to the initialization. And second, second I'll be sloppy because otherwise I would have to write a long formula and take a long time to write it. But second will be the following, that if you look at the test error, so this tells me something about optimization, but this doesn't tell me anything about generalization, about how this model behave of new test point. Okay, but one can prove, that basically under that assumption, this is what? This is the test error evaluated on the true model that you obtain by running gradient flow. This will be equal to the test error that you achieve by fitting a linear model, and I'll explain in a minute what I mean by this, where I run gradient flow on the linearized risk, plus a small error, and the error is small. So I want to write precisely what is this, also because I didn't write it in my note, but you can see. So one reference for this lecture is that there exists a review paper by Peter Bartlett, myself, and Sasha Racklin that you can easily find, and there is a version of this theorem that is, contains a precise bound here. Okay. So if you're curious about what is this error term, you can look at it there. Okay. Now, what instead I want to So what this theorem says, optimization is great, works great. You converge to a global empirical risk minimizer, and if you want to compute the test error of the model that you compute, you only need to compute the test error of a much simple linear model. And now I want to describe what is the linear model. And I'll take this theorem as kind of the justification for what I'll do in the following of this class, that is focusing on linear model. Okay, so let me describe what is the linear model. Yeah.
So can you get some intuition why you're guaranteed to flow to the closest theta on the manifold, the gradient flow?
Well, it's not necessarily the closest. This I didn't prove, but you converge to a point on the manifold, and okay, you can. There is a third point of this theorem that bound the distance, but you can get it. This is this boundary prime that we got here, basically, or R that we got here. So if you do this calculation, you get a bound on theta minus theta 0. So what I prove really, so what did we prove really? We proved that there exists this manifold. And if you start at the initialization theta 0, you will converge to a point here. I mean, what we proved is that there exists, if you trace a ball of radius r around this point, where r satisfies this, you can find it by simple calculus. I will not, you can do it by yourself. If you trace this ball, then there exists a point that is an interpolator inside this ball. So this manifold intersects this ball, right? If you go through the proof of this theorem, it's really a simple proof, but the proof of this theorem is not much more complicated than what we did. Shows also that you converge to some point inside this ball. Now, this point needs not to be, and in general will not be, exactly the closest point to theta 0 in the manifold, but will be, close to the closest point in a sense, right? Because what's happening is basically, okay, why is the closest point in L2 norm? What's happening basically is that the intuition is that you are approximating the risk, the function by the function class by a linearly parameterized function class, and this is what I explain in a minute. So the empirical risk becomes quadratic, and you know that if you do gradient flow in a quadratic function, I think Nati must have said this, you converges to the closest L2 point, right? So since you are linearizing anything, right? Does that make sense? So this is in this linear or lazy regime, the inductive bias is really L2 on the coefficients. Okay, let me write, and does that clarify the question? Thank you. So let me just write what is this linear model that is the most important missing fact of this statement. The linear model is the obvious thing, right? Is the first order Taylor expansion around theta 0 of the model. So I just do what I said in words. I'm just expanding to first order and truncate it. So this is linear, not in the sense that it's linear in X. It's linear in the sense that it's linear in the parameters. That is, of course, what matters for the optimization. Okay? And what is now this theta lin T? So this is gradient flow with respect to the risk for the linear model. Okay, let me perhaps erase this picture. Gradient flow with respect to R hat n of the linear model. Which is what is 1 over n. Or whatever you have here. And more conveniently, I can write this as 1 over n times the norm of y minus f n theta 0 minus the Jacobian, or perhaps I'll write it y tilde, minus the Jacobian at theta 0 times theta minus theta 0. No? So I'm approximating, my loss is a square loss. I'm approximating the model by linear model, so obviously what happens is that the cost function becomes a quadratic function. The empirical risk becomes just a quadratic function in theta. Any question about this? Okay, so this is basically what I want to say about optimization. And now one has to take a specific model to start making progress on generalization. And, or perhaps one doesn't, but the model that I'll focus on a very simple 2 layers neural network model. Okay, so this is a 2-layer neural network in which I'll simplify my life by fixing all the AIs. So I'll take A1 equal to A2. This will be +1, and the other to be equal to -1. So half of them will be +1 and -1. And instead, I'll fit the W. So my vector theta of parameter theta will be just W1, W2, W capital N. Okay, so capital N is the number of neurons. Okay, and my initialization, so these are learned. And my initialization will be that Wi0 will be uniform. Okay, and so this is the unit sphere in the dimension. And for simplicity, I will always neglect f of theta 0. That is, in this thing, I will drop this term. There is 2 reasons why it's okay to drop this term. First of all, is that this just is something that is not fitted, is a random function that doesn't depend on the data. So neglecting this only amounts to redefine y by y minus f of theta 0. So this is y tilde. And the second is that you can actually set it equal to 0 if you take, so can be set to 0 if I take a special initialization that is Wn over 2. If instead of taking this IID, I take the first n over 2 of the W IID and the other n over 2 equal to the first n over 2. Okay. So this is a specific symmetric initialization in which the first half weights are random and the other are copies of the first half weight n over 2. Of course, when you train them, then they do whatever they want. Okay? But if you fix them in this way, then the initialization, the function is exactly 0. Okay, so this is the model that we want to look at, that I want to look at. And I want to understand generalization in this model in the linear regime. Okay. course, this is something that would be interesting to do for multi-layer networks or for other architectures. And so there is an infinite list of open problems here that you can attack here, because this is really the simplest possible model. Okay, so the crucial thing is the gradient, in this thing is the gradient of the function at the initialization. So let's compute the gradient of the function of the initialization. All right? So this vector theta, so what is the number of parameters? Each of these is a vector of length d. There is capital N of them. So the number of parameters in this model is the number of neurons times the input dimension, right? So what is the gradient here? Well, it's obtained by stacking the gradients with respect to each of the w's. So okay, there is a factor 1 over square root of n. And then there will be, when you take the gradient here, let's say that you get a1 times sigma prime of w1 transpose x, x transpose, and then blah, 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 n times sigma prime w n transpose x times x transpose. So this is my gradient at initialization. Okay, and so the linearized model perhaps I should write it instead. So let me write it in terms of the difference that I'll call B. Let's leave theta 0 understood. So this is at initialization. Okay, so let's compute it in terms of the difference. This will be 1 over square root of n sum over I 1 to n. And then there will be ai and then bix sigma prime of w prime wi x. So B is the difference of theta and theta 0. So I should mention that the first, actually there is a paper even earlier that has something of this, but the first people that looked at this specific model were a group of physicists, mathematical physicists at EPFL, so Jacob, Gabriel, Hongler, that also invented I think the catchy term of neural tangent. Okay, so this is my model. I can always redefine the b's. This is a plus minus sign. I can reabsorb this in the I here like this, and actually I'll put a factor square root of d here because it's convenient. And what is this really again is b times phi of x, where phi of x. So you can think of this as a model in which you take your data, you compute a feature map that is phi of x, that is a nonlinear map, and then you multiply it by this coefficient. And my feature map is really that one. It's 1 over square root of nd times sigma prime w1 transpose x, x transpose blah, blah, blah. Okay. And okay, so what I'm interested in here is computing the risk of this, where B's gradient is trained by minimizing the risk here. So I want to look at B hat, that is argmin of L2 norm of B, subject to B times phi of xi equal to yi for each I.
Sorry, how did you drop the AI?
I just redefined B to be B times AI. Since the AI are plus minus 1, this is okay. This doesn't change this L2 norm. Of course, if this AI were not plus minus 1, then this would twist a little bit my L2 norm this definition, this change of definition, right? But this is the reason why I chose them. That shouldn't be too important, from a qualitative point of view, but simplifies a little bit my calculations. Okay, so I'm interested in the generalization error in this model in which B hat will be computed this way. Any question? Okay, so before we go there, we start our work, you should have asked me one question, right? So you derive this general condition. So the general condition was ln times y tilde less than sigma min phi square over 4. And the question that you should ask me is, does this condition hold for your model? That's a pretty natural question. So, okay, there are computations based on these conditions for many models. They are never, precisely tight, but I think, okay, the best result for this model. So let's for simplicity is, okay, assume a simple model for the data. So X will be, let's say, normal 0 ID. And the model, as I said, then, and okay, yi of order 1. Then, this condition holds with a probability if ND is bigger than some big constant times n square. So I should say this condition in abstract terms, as I wrote it here, was first appeared in a paper of Shizai and Bach. And this result that I'm quoting here is based on, so how do you check this condition? Well, basically you have to lower bound the minimum singular value of the Jacobian, and you have to upper bound the Lipschitz constant of the Jacobian, right? So you need a lower bound here and an upper bound here. And this, once you have these two bounds, you plug them in this condition and you get this. This is all explained in this review paper. And the specific bound that are used to get this are, for instance, in a paper by Oimak, Sameto Mak, and Madi Soltano Kotabi. Tano Kotabi. And yeah, so this is the best bound available for this two-layer neural network. It's not completely, is it completely satisfactory? Well, not really, right? Because hopefully we would like to catch the whole regime in which the number of parameters is bigger than the sample size. But this requires the number of parameters bigger than the square of the sample size. Okay? So there is a gap there. And the computation that they do of sigma mean is tight up to constants, but the whole computation has a gap. Now there is a remark that is in this paper of Shizabak that is the following. If I replace here by this constant 1 by alpha, so if f is equal to alpha over square root of n times sum over I ai times sigma of wi transpose times x. Okay, I simply scale my model. Then how does this affect this condition here? Remember, this is basically the second derivative of f, so it's proportional to f. So this gets a factor alpha. But this is the first derivative of f, and you are squaring it. So this term gets a factor alpha square. So this condition, it's not invariant under scalings of f. It's invariant under scaling of theta, but it's not invariant under scaling of f. So if you plug this in here, this leads to is sufficient in this specific setting to get ND, and in fact in okay. So what does this mean? That if I take alpha large, and I need to be over-parameterized, so I need there to be solutions. But okay, let me gloss over it. If I scale alpha large enough, then I will always be in the linear regime. Okay, so this is why they coined this term lazy, I think, lazy training, because to say, okay, it is really not a special property of neural networks. Any model, if you scale it in a certain way, any nonlinear model that has some homogeneity properties, if you scale it in a certain way, since it's just a consequence of this fact that this is not invariant under scaling. So if I let alpha grow, this thing grows at rate alpha squared, this grows at rate alpha, so at some point it will be satisfied. Yeah?
So if you scale alpha, wouldn't the norm of like tilde also grow?
Okay, yeah, good point. So this is true if y tilde, if f at the initialization is 0. If f at the initialization is 0, then y tilde is equal to y, so it doesn't depend on the scaling. But you're absolutely right. If you put y tilde, then it might be that this condition is not satisfied, even for large alpha, if you don't take this initialization. Okay, so the upper bound on this Lipschitz constant will not do, but lower bound on the sigma mean will be a consequence of something that I will talk about. Okay, so what is the plan now? Any other questions, perhaps? Yeah.
Yes. If I do this rescaling, does the generalization or training error gets rescaled too? And thus it's like a scale in the system that I'm putting or modifying?
If you are in the linear regime, then the generalization error will not change, right? Because putting an alpha here, you can always reabsorb in the B, right? The alpha. So as long as you are in the linear regime, that will not change, of course. Any other question? All right. So okay, so very nice. We convinced ourselves somehow with a bit of wishful thinking that all that we have to study is linear regression, and, which actually is quite interesting, turns out. So what I'll do in the next lectures is I'll proceed in the following order. I first look at linear regression or ridge regression with a simple random feature. So I'll explain what means. And describe some interesting things, unexpected things that happen there. Then move to kernel ridge regression, and then move to neural tangent regression. That is really what I'm describing here. So I could skip directly to chapter 3, but in the end you'll see that chapter 3 is very much related to chapter 2. In fact, the results, basically the results of this chapter says that you get the same risk as in this chapter. And I think that looking at the simple random feature models really gives a lot of interesting intuition, so it's worth doing. And after this, if I have time, I'll do something. I don't know what I'll do really, but I didn't yet prepare. So I have a few options, but suggestions are welcome. Let's put it this way. Okay. Okay, so let's get started on simple random features. So what I mean by this, yeah.
And all that you said you would be focusing on the square laws? Or?
Yeah. Yes. I mean, okay, so some of these things, can be generalized or have been generalized to other losses, right? In particular, the first bullet point. But not to the, first of all, not to the degree of generality that have been done to square losses. And then, in my opinion, for other losses, it's hard for me to tell what you really learn new beyond what you learn for square losses.
Okay, so you expect that it won't be crucially different
Right. If you take other convex losses, yeah, I mean it's.
beyond being harder to
Yeah, I mean, but it's I think it's worth. But I think I'll focus on the basics because most the first works, and I think a lot of intuition was gained for square losses. So I'll really focus on that, I think. So what we want to study, so let me generalize a little bit what I was saying somewhere here. I want to do mean-norm regression. Perhaps I should call this B instead of beta. So I want to do minimizing over beta in RP of what? 1 over n y minus z b square plus lambda b. Of course, I said that I want to do the minimum norm interpolator, but this is obtained by taking lambda to 0. So if and so ideally, so Z here is a matrix Z1 to Zn. N by P. And ideally, what I want to take is Zi to be this feature map applied to Xi. But what I mean by simple random features is that I consider a simpler model here. Okay, so but before the model, let me say some generalities about ridge regression. Some simple things about ridge regression. So first simple thing is that you can write the solution of that optimization problem, of course, explicitly. And this is 1 over n Z transpose lambda I plus 1 over n Z transpose minus 1 times y. Okay? So this is completely explicit, which simplify my life. And we can write also the risk quite explicitly in terms of the matrix Z. If, for instance, we assume a simple model for the data, so let's say that we take the data to be beta star transpose times xi plus epsilon I, where epsilon I is noise. Okay, this can be generalized, but oh, this is not xi, but zi. Okay, and let's say that the zi, let's define sigma to be the covariance metric of the zi. Then the risk, this is the test error as a function of the data and of the regularization parameter. Okay, this is, as usual for square loss, this is the sum of a bias term plus a variance term. Okay? You know this, right? I mean, the bias term is simply the... Okay, what is this? This is f minus f hat L2 norm square. This is the risk. It's the square error, so it's the L2 norm of f minus. So this is f minus, the bias is E of f hat and the variance is f hat minus e. Right, so this is just Pythagoras theorem.
The expectations are over.
Okay. Over the new point. Oh, I don't need expectation here, right? Because it's in the L2 norm. The expectations are over the new point.
Over the new point, but the features are fixed.
Right, so here, these are, I trained this, right? So here I'm looking at the risk given the data points. Okay, so perhaps I'll write, let me write this more explicitly. Okay, so let me write. So what is the risk here will be the expectation over what I want to write. Z nu, and I'll take also the expectation over epsilon 1, epsilon n. Yeah, you could, this expectation we always take, right, when you do the test error. And the expectation over the noise in the training, you can put it or not put it. Here I put it just to simplify some formula. If you don't put it, you can prove that it concentrates, so it doesn't really matter. And of what? I'll look at the excess risk. So beta hat lambda times z nu minus beta star times z nu square. I could add also plus epsilon nu, but that adds also only an extra term, additional term sigma square. So this is the risk, and it depends on the matrix Z on which I trained, just because beta hat depends on the matrix Z. I could entirely drop this, but okay, I would get a slightly more complicated formula. Okay? Okay, so I claim that this is, so let's forget a moment what this thing. So of course this you can also write as the expectation over epsilon 1, epsilon n, and take the expectation over the new thing, right? So this is the same as beta hat lambda minus beta star sigma norm square, where a sigma norm of a vector is just vector sigma vector. If you expand the square and you take the covariance of the z, the covariance is z, so it's just this guy. Okay, and this you can write it as, so b star doesn't depend on this, so you can write this as b star minus the expectation over the epsilon of b hat sigma norm square plus beta plus the expectation of and this is always with respect to the epsilon. Right? So this is the bias, and this is the variance. Okay? And there is no cross term because, okay, you compute it and there is no cross terms. Because the expectation is just L2 projection, it's just a projection. Sorry?
There is not the epsilon mu.
Well, you could add here, instead of this, one other, the way I defined originally the risk would have been beta hat lambda z nu minus y nu. So what is the difference between these two? Where y nu is just bit star times z nu plus epsilon minus epsilon nu square. And this is just this plus sigma square, where sigma is the variance of epsilon. So this is sometimes called the risk, and this is the excess risk, meaning is the risk over the ideal predictor. But they differ just by a trivial term. So the risk will not go to zero, will never go to zero, because you will not be able to predict the noise, but the excess risk might go to zero. Okay, what time is it? I have 5 minutes. Okay, so perhaps 5 minutes. Okay, now we have this thing. So this is the bias, z lambda, and this is the variance. Perhaps I wrote it in the opposite. No, yeah, the variance z lambda. And okay, you can do a little, you have now this formula, you plug it in here, you do a little 5 minutes algebra, and you obtain the following formulas for the bias and the variance. This is lambda square times b star times s lambda, and I'll define this object in a minute, s lambda b star, and the variance. This is sigma square over n, and then the trace of sigma hat as lambda. And what are these objects? Sigma hat is just the empirical covariance, z transpose z. So this is 1 over n sum over I, 1 to n, zi transpose. So this is the empirical covariance of my Fisher vectors. The expectation is, of course, z. And S lambda is an important matrix. It's just the matrix that shows up here, right? So this is lambda I plus sigma hat inverse is the resolvent, or okay, so this is thing. Now we want to compute these two objects, and as you see, these are random matrices. So you can do it by random matrix theory. Now, one important thing is that what matters is not the eigenvalue. It's not only the eigenvalue distribution of these matrices, but is also the eigenvectors, right? Because what we are looking at is for instance, we are sandwiching this random matrix between two vectors, so the value will depend also on the eigenvector of this random matrix. Okay. Okay, you know what? Perhaps I'll stop here and I'll do it in the next lecture. I'm about time, and perhaps I'll leave pause for one question if there is any. Nobody want to take the role of stopping the other from going to lunch. But
Yeah, 50
I have a really quick question actually about your first part. So you define this like Lipschitz constant and the Jacobian in a global way. You only use it locally. So presumably everything that you just have it in a ball, nothing can stop you from running the same argument.
yeah, absolutely. So good question. Can you see the weak part on this argument is that one, is that Lipschitz constant. Yeah, so either in a local way or even in a directional way, right? Because we don't necessarily need the whole ball, but we need it only ideally along the direction that leads to the thing, right? So yeah, it might be that one can improve that n square bound that way. I didn't try. I don't know if somebody tried. Yeah, but yeah, that's a good thing to try. Somebody should. Yeah, I think that the jury is open whether there is an intermediate regime where the model has more parameters than observation, but this lazy training doesn't work or not. I mean, if I had to bet, I would bet that perhaps modulo constant there is no intermediate, or modulo logs there is no intermediate regime. I mean, my blind guess is that this n square is a proof artifact, but I might be wrong. I think it's a very interesting question. Okay, if not, thanks.